I'm Umutcan Kılıç from Boğaziçi University in Turkey. Today I will present you our study on latency aware construction activity recognition using kinematic and physiological sensors. So construction environments are characterized by their dynamic and hazardous natures, and recent studies have explored the use of physical and physiological monitoring of the workers to mitigate some of these risks. Human activity recognition in this regard has become a prominent tool, allowing the automatic detection of the worker activities, movements and postures using several approaches. It can be mainly split into two categories, visual and non-visual human activity recognition systems based on the data utilized. So offering cost, privacy and robustness advantages, the non-visual human activity recognition systems are especially attractive for construction environments. However, there exist some limitations in the existing systems. They usually rely on inertial measurement unit-based kinematic data. So these kinematic sensors are very effective in capturing the movement, its direction, its magnitude, but they provide very limited insight in the actual reaction of these movements on the worker's body, including the physical exertion, fatigue, and physiological systems. So maybe using these physiological data signals, we can complement the already existing kinematic data sets to enhance the performance of these human activity recognition models. But there exists a problem. So the kinematic reactions almost immediately respond to the movement. So like as soon as you start walking, the inertial measurement units are able to capture this movement, but physiological signals respond with something called biological latency. So it depends on the type of the data, but for cardiovascular responses, it occurs within a few seconds, and for electrodermal responses, it usually occurs 2 to 6 seconds after the onset of the stressor. So the problem is the usual timestamp-based fusion of the data sensors might create a mismatch between the physical action and the corresponding biological reaction, creating a noise rather than enhancing the model's performance. So we aim to investigate different temporal alignment strategies to enhance the model. So we compare different data modalities, different windowing approaches, and we introduced an artificial time lag in order to align the physiological reaction with the actual corresponding physical activity. And as an output, we tried to get a latency-aware fusion protocol for multimodal worker monitoring systems. For that reason, we conducted a controlled laboratory experiment with 5 healthy male subjects. We collected data during independent experimental sessions, and you can see their demographic information on the table on the right. During these experimental sessions, we utilized 2 devices. So one was a smartphone located at the lumbar region using an adjustable vest. We also had a smartwatch located on the non-dominant wrist. So the smartphone was recording accelerometer and gyroscope data, whereas the smartwatch was recording physiological and some kinematic data. We also recorded the sessions using a chest-mounted GoPro and also a smartphone for the data labeling purposes. The participants followed an experimental setup. We started with a 5 minutes of physiological baseline calibration period, followed with 4 identical activity vlogs, including very common activities such as walking, stair climbing, ladder climbing, material handling, moving weights with a pallet truck, etc. And also we allowed them to rest for 2 1-minute blocks after the first 2 activity blocks and at the end of the experiment. For the ground truth annotation, we used Elan software, and we manually annotated the activities relative to the video timeline. Then we, using this video relative timestamps, we converted them into Unix timestamps to align the sensor data with the videos. We used a sliding window approach and 75% consensus rule, where an activity label was given to a window if the underlying 75% of the underlying activities was coming from a single activity source. So these are the activity types and their corresponding labels. Then we extracted features for each windows. and we normalize the level-dependent biological signals using a z-score standardization, where the mu and sigma was calculated over the sitting rest period. We tested this approach over 4 different window sizes, 2 different overlap ratios, and 8 different physiological delays. We modeled 6 different sensor configurations and trained random forest classifiers with 103, so it resulted in 240 different model configurations. And we evaluated each model using a loss across validation, and we also reported several performance metrics. So when we look at the results, so these are the performance of the simple fusion strategy, where we do not have any did not have any temporal alignments. So the physiological sensors were simply added using the actual timestamps of each activity. We see that the physiological only model was performed very terribly. So it was a bit only better than a random classifier. And we can easily conclude that physiological data only is not able to classify 7 fine-grained activities. For the simple fusion, the best configuration was actually smartphone and smartwatch only kinematic data, so without the inclusion of the physiological sensors. But adding the physiological sensors without any temporal delay actually slightly reduced the performance, meaning that if we do not account for this biological latency problem, then we introduce a noise to the model instead of providing additional information. Then we compared the fusion model, where we combined all of the sensor modalities, including the kinematic ones and the physiological ones, across different temporal delays and across different window size and overlap ratios. We observed that the best performance occurred when we used the 8-second 75% overlap window with 4-second biological delay. However, the simple fusion counterpart of these systems, where we introduced no delay, performed a bit worse and had a higher standard deviation across the faults. And further increasing the delay degraded the performance, indicating that so there exists a temporal shift between the activity and the corresponding reactivity, and if we keep increasing the biological latency, we once again add a noise to the system rather than improving its performance. Lastly, we compared the confusion matrix and class-wise performance metrics for the best performing model and its simple fusion counterpart, where we noticed both of the systems showed a strong diagonal performance. However, the latency aware fusion model mainly improved the cart and walking activities, where the number of misclassified activities for cart, like walking activities misclassified as cart, decreased from 50 to 8. And as a result, the precision and also the F1 score for cart activity significantly increased. So why did this occur? The two activities has very similar kinematic patterns and very similar body postures. However, one, the cart activity, where the people were pulling approximately 100 kilograms pallet truck, they experienced a higher exertion level, meaning that the added information actually helped us better classify these two kinematically similar activities. So our key takeaways are the temporal alignment in fact affects the multimodal human activity performance. The best performance occurred when we used the 8-second window with 75% overlap and 4-second physiological delay. So the temporally aligned physiological data can in fact add another layer of information for the activity detection. And without the temporal collection, the physiological data might become a noise rather than informative input. But this study has several limitations, so we conducted this test in a controlled laboratory setting. We had a very limited activity set, and we also had a very limited sample size of 5 male subjects. So future validation with more diverse activity classes, more diverse participants, and also maybe the training of this algorithm with an in the wild construction setting might be required to further validate these results. So these are some of my references. Thank you for listening.